I welcome you all to this session of engine system and performance, and the topic of our today's discussion is energy transfer mechanism from engine cylinder or combustion chamber and the components involved. If we recall, in the last class we have discussed about the need of transferring energy from the engine cylinder, and we had seen that energy is supplied into the engine through fuel. Fuel is having stored energy within it, and that chemical energy essentially gets transferred or transformed into another form of energy, that is mechanical energy, which is or which will be available at the shaft. Now, that conversion from chemical energy into mechanical energy is not possible directly. So, what we had seen, that combustion is there, and through that process, which is indeed a complex process, several thermodynamic processes are involved. As such, to know more about combustion, you need to know two fundamental subjects, that is thermodynamics and fluid mechanics, and also heat transfer. So, that energy which is remaining stored in the fuel, that is the chemical energy, has to be converted into useful form of energy, that is mechanical energy. And as I said, this conversion is not possible directly. So, essentially what is done, that chemical energy is converted into heat energy by virtue of combustion, and then that heat energy is getting transformed into another form of energy, mechanical energy, which will be available at the shaft through some mechanical arrangement. And as you know, that heat energy is a low grade energy and work is a high grade energy. Essentially, it is not possible to convert heat into equal amount of work. So, what I mean to say, the energy that is being supplied, that is chemical energy, into the engine, that energy will be converted first into heat, and then again that is not possible to have equal conversion, and finally heat would be converted into work. So, again there will be some sort of reduction. So, what we have discussed in the last class, that total power generated, W dot power equal to W dot shaft plus Q dot loss plus Q dot loss through exhaust gas plus W dot parasitic. That is what we had seen in the last class. So, you see, this is the useful energy or work available at the shaft, right. This is also to some extent, I should say, useful, because this is also needed. So, this part is used to run several auxiliary systems. like air conditioning unit, several lights to run a small pump, all these things. So, if we look at that energy supplied to the engine is m dot f into q h v, mass flow rate of fuel and multiplied with heating value of the fuel. So, this is heating value of the fuel being supplied, and this is mass flow rate of fuel. So, out of this energy, which is nothing but the chemical energy which is remaining stored in the fuel, we are essentially getting this much of energy, useful energy. Certainly this is also used, but that means this part is totally getting lost. These two parts are getting lost, loss of energy. So, this is loss of energy. So, this is loss of energy, and what is this? This shaft work is essentially m dot f q h v eta break thermal and eta combustion. So, this is the expression of the useful work which is available at the shaft. So, that means essentially this minus this, that is m dot f. So, this m dot f into q h v into 1 minus eta v into eta c. So, this is break thermal efficiency, this is combustion efficiency. So, this is combustion efficiency we have discussed this aspect in the last class, and that is break thermal efficiency. So, this amount is of no use, right. So, that is essentially, I mean, if we remove this parasitic load, that is essentially q dot loss plus q dot loss through exhaust gases, right. Now, this fellow has 3 sub components. So, that means this part is loss of energy through exhaust gases. That means, when combustion gases are leaving from the engine cylinder during exhaust stroke, those gases carry certain amount of energy in the form of enthalpy and also chemical energy, and those gases are also removing some energy from the combustion chamber, right. But this is q dot loss, that is the that part is significant. It has 3 sub components. It has q dot coolant, that is we need to supply coolant. If it is a water cooled engine, we need to supply water through cooling outer jacket, and that circulation of water carries or removes substantial part of energy from the combustion chamber or engine cylinder through the wall of the cylinder, and that is that part is basically 10 to 30%, that is what we have discussed, plus we have q dot oil, plus we have q dot ambient, right. Q dot oil is not very very high, that is 5 to 15%, and this is 2 to 10%, and this is 5 to 15%. So, you can understand that substantial amount of energy will be removed by the coolant from the engine cylinder what this part is all about? Q dot oil, you know that if you try to recall, we have discussed that we need to supply lubricants to have, in fact we have lubricating system, and that lubricants are splashed over the piston. In fact, lubricant I should say, lubricant is splashed over the piston face so as to remove certain amount of heat from the piston face itself. Try to recall, in the last class we have mentioned that there are a few surfaces or spots which are having high temperature, and those surfaces and spots are piston face, spark plug area, exhaust valve, and to some extent intake manifold. So, that means we should have, or the engine should have, an arrangement to remove certain amount of heat from the piston face so as to increase the life of the piston, and that is why the lubricant oil is splashed over the piston face so as to take away certain amount of heat from the piston face. As I said you that combustion is the process through which rise in temperature inside the cylinder is of the order of 3000 Kelvin. If we really do not have, in fact we should have proper design, and engine should have some arrangement so as to remove substantial amount of heat from the engine cylinder to prevent several components from overheating, to prevent several mechanical components from their possible failure, in fact to prevent mechanical components from melting. Over and above, if we really do not transfer adequate amount of heat from the engine cylinder, lubricating system or lubricants will lost their ability to lubricant or provides enough lubrication to the system. Now, what about this ambient I will be discussing. So, you can understand that we need to transfer this much amount of energy from the combustion chamber. So, let us discuss now heat transfer in the combustion chamber. Okay. So, this is very important, heat transfer in the combustion chamber. Now, combustion chamber is the place where rise in temperature is of the order of 3000 Kelvin, that is what we have discussed, right. So, let me write here that rise in temperature of the gases in the combustion chamber of the order of 3000 Kelvin, right. So, we need to remove substantial amount of heat so as to reduce the temperature inside the cylinder. Now, there are three principal modes of heat transfer. What are those? So, modes of heat transfer are convection, conduction and radiation. So, these are the three principal modes of heat transfer. Now, when fuel evaporates inside the combustion chamber as a part of the combustion process, that process of evaporation also is involved to some extent with the heat transfer, evaporative heat transfer. So, this convection, conduction and radiation. Now, these three are the three principal modes of heat transfer. Now, let us look into this is not that much significant, but still we really cannot trivially ignore the radiative transport of heat. So, we have to now look at these two different or these two principal modes of heat transfer inside the combustion chamber. So, let us now consider, you know that when we need to, or rather when engine is started during first a few cycles of engine operation, whether it is an automobile engine or a large stationary engine or small stationary engine. During initial a few cycles of its operation, fresh air is inducted, or if it is SI engine, fresh charge is inducted into the combustion chamber. During that time, it may be a case that temperature of the inducted air or fuel air mixture is even less than the wall temperature. So, in that case heat will be transferred from the wall into the inducted air fuel mixture or air, but when combustion starts, immediately temperature increases and temperature becomes so high that convective transport of heat initiates and results in this convective transport of heat results in transport of heat from the gases of from the gases inside the cylinder into the inner wall of the cylinder, and cylinder wall will be having certain thickness. So, from inner wall to the outer wall of the cylinder, conduction will play an important role, and finally, in the outer wall of the cylinder, cooling water jacket is incorporated or installed or integrated. Now, the part of the cylinder which is in contact with coolant, which would be circulated continuously, again convective transport of heat will be there, and finally, entire length of the cylinder wall will not be under the influence of coolant. So, a few portions will be directly exposed to the ambient. So, from there outer surface of the cylinder wall heat would be removed again by virtue of convection, but directly into the ambient. So, now let us discuss about this convective transport of heat, or let us identify where convection play an important role and where conduction plays an important role. So, let us draw the schematic. So, just if we draw the schematic depiction of the engine cylinder, first that is intake manifold. So, we will have spark plug, and this is the piston, say this is bottom dead center, this is top dead center, this is exhaust valve, this is intake valve. So, now if we zoomed in the cylinder wall, so basically you know that this is the cylinder wall, it is having finite thickness, say this is delta x. Okay. So, if we take this is x direction, now this is cylinder wall, and cooling water jacket is provided to take away heat from the cylinder or combustion chamber. So, this is coolant in, coolant out. So, this is cooling water jacket. So, if it is a water cooled engine, and now again we will be having, so this is the inner wall of the cylinder, so temperature is TW1, and this is outer wall of the cylinder and temperature is TW2. And So, this is temperature of the gas T g. So, only we have taken this part. So, let me we have taken this part only to show the cylinder wall arrangement. So, now, this is the combustion press. So, this is the combustion space. So, when combustion occurs, this T g is of the order of 3000 Kelvin. Certainly, it is not needed that 3000 Kelvin should be transferred. I mean, we need break thermal work. So, this the moment when combustion occurs, the rise in temperature initiates convective transport of heat from the combustion gases to the inner wall of the cylinder. So, let me tell you one thing, T W 1 should be T W 1 should be within 180 to 200 Kelvin, right. So, that means T g is of the order of say 1000 Kelvin. So, immediately convective transport of heat will initiate or occur from the combustion gas S to the inner wall of the cylinder. Now, certainly we need to maintain this much amount of temperature at the inner wall of the cylinder, essentially to keep cylinder material or other different parts from overheating. So, then from inner wall of the cylinder to outer wall, heat conduction will be there, because this is of any material that we have discussed in the in one of the previous classes. And then finally, what I wanted to say, you can see that these two parts are not in contact with the coolant. So, through which from these two surfaces again heat transfer will be there to the ambient, right, and from the outer wall which is in contact, the outer wall portion which is in contact with the coolant, there again some convective transport of heat will be there, and that convective transport of heat will be solely dictated or guided by the flow of coolant. So, from the outer wall of the cylinder, convective transport of heat is, or convective transport of heat or transport of heat, convective transport takes place from the outer wall to the coolant, from the outer wall to the ambient directly, and the convective transport of heat from the outer wall to the coolant will depend on the coolant circulation or flow velocity of the coolant, convective heat transfer coefficient of the coolant, and also the convective transport of heat from the portion which is, or from the portions which are not in contact with the coolant will depend on the ambient air temperature and also the convective heat transfer coefficient of the ambient air. So, these are different modes of heat transfer inside the combustion chamber. Again, since the temperature of gas is too high, we really cannot trivially ignore the radiative transport of heat, which is solely due to very high temperature difference. So, this is all about for a water cooled engine. Now, if we try to draw an air cooled engine, so if it is air cooled engine, if it is a air cooled engine, so you can see So, if it is delta x, so this extended surface, so fins, so these fins are provided so as to enhance the transport of heat, because airflow will be there over these fin surfaces, and that air circulation will allow more convective transport of heat from the outer wall of the cylinder to the air. Exactly here the same. So, here again, so this is TW1 and this is TG, and finally from TW, so this is TW to T air, right. So, this is basically these two different types of cooling systems that we have discussed already. Now, let me discuss about the mathematical expression of heat transfer, or I mean, if we really would like to calculate the amount of heat will be transferred by all these processes, we need to go for computation. Essentially, if we need to go for quantification, but qualitatively we can express the amount of heat would be transferred by all these processes from the engine cylinder into the ambience. So, what we have discussed? So, first of all, the convective transport of heat would be there from the gas into the gas to the inner wall of the cylinder. So, from gas to the inner wall. So, if it is q dot 1 that equal to H G A into T G minus T W 1, right. Heat transfer across the wall. So, this is again q dot 2. If we write, then it would be K A and delta T divided by delta X, right. So, where this delta T is T W 1 minus T W 2. So, this is the thermal conductivity of wall material, right, and this is convective heat transfer coefficient of gas. Okay. So, now this is so let me write here. And then finally, from outer wall to the coolant. So, this is q dot 3 equal to again H C A into T W 2 minus T C, and heat transfer from the outer wall to the ambience, that is q dot 4 equal to H A into, now this A, this is the surface area which is not in contact with the coolant flow. So, this A surface area which is not contact with coolant flow, right. So, these are the expression. Now, let me write, if we sum up all this expression, then we can have as such, you know that this is not very significant, because if we look at the schematic depiction, only a very small portion or portions are exposed to, you know, ambience. So, basically if we do not consider even this, but theoretically we should consider this part as well. So, now what we can write, that heat transfer through the cylinder wall per unit area. So, heat transfer through the cylinder wall per unit area. Okay. So, Q dot equal to capital Q dot by A equal to T g minus T c, I should write, divided by 1 upon H g plus delta x by k plus 1 upon H c. So, try to understand, in this expression we did not consider this quantity. As I said you that theoretically this quantity should also be taken into account when someone is designing the engine block or engine heat transfer, heat management in engine. But as I said you, from the schematic depiction, that was clear that portions which are not in contact with the coolant flow is not, you know, rather is insignificant, and also convective transport of heat, because there is no air flow. So, as compared to the transport of heat by the coolant, that part is trivially or insignificant. So, that is why in this expression we did not consider that part. So, here you know all the terms, because T g, T c you know, T c is the coolant temperature. So, here we have written T c is the coolant temperature, right. So, this is the coolant temperature. Now, this is the expression. Now, the speciality of this transport of heat is, this is basically cyclic heat transfer. So, I am writing the word cyclic heat transfer. Why cyclic heat transfer? Because you know combustion will occur in each and every cycle, but and that is also, you know, that whenever combustion will be there, then only maximum amount of heat will be transferred. For the remaining other strokes, that, you know, this much transport of heat may not be needed. So, that is why this is cyclic heat transfer. Now, I would like to discuss a few important things, that here T g, would we like to consider T g constant? No, T g will vary across the space of the combustion chamber, that too it will vary over an engine cycle. So, this T g is not constant, it will vary over an engine cycle and across the, you know, breadth and width of the combustion space, or let me write, it will vary over the engine cycle and within the cylinder, right. So, this is very important to know, within the cylinder. What about H g? This H g also not, it is also not, it is not constant, because this will also vary over an engine cycle and it will depend on the formation of swirl, turbulence and also gas motion, because you know the convective heat transfer coefficient, as I told you that even if we consider coolant flow, convective heat transfer coefficient of coolant, that will also depend on this velocity of the coolant flow. Similarly, this convective heat transfer coefficient of gas is not a constant, it will vary, rather it will greatly vary, I should say largely vary over an engine cycle. Quite obvious, you know, that during combustion convective transport of heat will be there, but when combustion is completed, still convective transport of heat would be there, but during that time convective heat transfer coefficient will not be the same as we should consider when combustion initiates, and depends on swirl, turbulence and gas motion. As I told you, you know that when combustion occurs, piston reciprocates between these two locations quite, you know, I mean spontaneously, and the gas motion inside the cylinder is highly erratic and chaotic, and if we could define Reynolds number, then certainly Reynolds number will indicate that the inside the flow is highly turbulent. So, depending on the, you know, or even swirl will form, that we had seen, probably you have studied in internal combustion engine course, that when main flame front develops, to you know increase the speed of the main flame front, we need to you know have some sort of you know circulatory or swirl motion inside the cylinder. So, depending on all these swirl structure, the you know kind of extent of turbulence inside the combustion chamber and gas motion, this convective heat transfer coefficient will vary. What about thermal conductivity? Thermal conductivity is function of temperature, right, but this is thermal conductivity of cylinder wall material. So, we can assume this is fairly constant, because you know that cylinder wall is having finite thickness and continuously coolant would be circulated to remove heat. So, we can assume that temperature fluctuation across the length or across the width of the cylinder wall is not that much high, so as to consider you know temperature dependent thermal conductivity. So, this is you know K is function of is a function of temperature, but is fairly constant, will be fairly constant. What about HC, convective heat transfer coefficient of the coolant? Again you know it will depend on the flow velocity of coolant, but we can assume that typically coolant flow is fixed, we can assume that convective heat transfer coefficient of coolant will remain fairly constant. So, we can assume HC will remain fairly constant, right. So, this is very important. Now, let me, why it is will remain fairly constant, because coolant velocity will remain almost constant. Now, let me tell you one thing, because we need to solve a few numerical problems. So, we need to understand, essentially to understand the transport of heat, not even if we go for quantification, at least qualitatively if we need to know the transport of heat due to convection, we should characterize or we should know flow characteristics. So, even for qualitative estimate of transport of heat, we need to characterize the flow, underlying flow rather, and also the heat transfer. So, to know or to understand flow characteristics and also the associated heat transfer, we must define Reynolds number and Nusselt number. So, to understand flow characteristics and associated heat transfer, we must define RE and Nusselt number are defined. What is RE? because if we define RE, then we can establish flow characteristics and associated heat transfer for different sizes of engine, for different speed of engine, all these things. So, why this is important? To characterize the flow and heat transfer for different sizes of engine, geometries and speeds. So, for different sizes of engine, for different geometries of engine and different speeds of engine, that is piston speed. So, R is defined m dot F plus m dot A into bore divided by A piston into mu g. So, this is mass flow rate of fuel plus mass flow rate of air, that is mass flow rate of charge divided by piston area, right. This is piston area, or this is area of piston face, and this is dynamic viscosity of gas inside the cylinder, right, and this is bore. So, this is Reynolds number, and then knowing Reynolds number, we can define Nusselt number, that is also very important, Hgb divided by Kg. So, this is thermal conductivity of gas inside the cylinder. So, this is thermal conductivity of gas inside the cylinder, that can be correlated like C1 Reynolds number to the Reynolds number power C2, C1 and C2 are constants. So, that means defining Reynolds number properly, which is very important to characterize flow for different sizes, different geometries and different speed of engine. We also can define Nusselt number, which will allow us to characterize underlying heat transfer even for different sizes, different geometries and different speeds of engine, right. Until now whatever we could discuss, that is convective transport of heat inside the cylinder, that is from the gases into the inner, or from the gases to the inner wall of the cylinder. Convective transport of heat so basically the Reynolds number and Nusselt number that we could define, that these two numbers are basically for the convective transport of heat inside the cylinder. Similarly, convective transport of heat outside the cylinder, can be just model using normal internal flow convection, and from there we also can define Reynolds number and Nusselt number. So, this convective transport of heat outside the cylinder can be model by conventional methods of forced convection. Right, for convective heat transfer, right. So, and from there we can define Reynolds number, Nusselt number. Now, finally, I would write that radiative transport of heat inside the combustion chamber. This is also, though it is not very significant, but as I told you, we really cannot trivially ignore because of significant change in or significant difference in temperature. So, this just I am writing again q dot per unit area, that is q dot by A, that equal to sigma into T g power 4 minus T w power 4 divided by 1 minus epsilon g by epsilon g plus 1 upon f 122 plus 1 minus epsilon w divided by epsilon w. So, this is the expression. So, as I said you that though this amount is not very substantial or very high, but still because of the significant temperature difference between combustion gas and wall, we have this amount through this mathematical expression. So, this is what is this? You know that sigma is Stephen Boltzmann's constant, T g is gas temperature, T w is wall temperature. Here epsilon g is emissivity of gas, epsilon g emissivity of gas, epsilon w that is emissivity of wall, right. F12 is view factor that you have studied in undergraduate heat transfer course between gas and wall, between gas and wall. Let me write, instead of writing F12, it would be right if I write G and GW. So, this is F GW, right. So, this is what is the radiative transport of heat. So, if we try to summarize our today's discussion, we have just discussed about the transport or heat transfer in combustion chamber, knowing the amount of heat to be transferred by the coolant, and then we have depicted schematically arrangement of the components rather, that is wall and also the cooling water jacket, and then we have identified several modes of heat transfer for both water cooled and air cooled engine. Then we have estimated all components, that is heat transfer, that is convective transport of heat from gas to the inner wall, across the width of the wall, that is conductive transport of heat, then convective transport of heat from outer wall to the coolant, and convective transport of heat from outer wall to the ambience directly. And then we have tried to sum up all this, then we got this expression which is cyclic heat transfer. We have identified that convective heat transfer coefficient of gas, conductivity of wall material, convective heat transfer coefficient of coolant, whether they are constant or they are they will vary, and then we could define Reynolds number based on this convective transport of heat inside the cylinder. From there we could define Nusselt number, just correlation. These two numbers are defined just to characterize the flow and associated or underlying heat transfer for different sizes, different geometries and different speeds of engine. Finally, we could see that if we need to define Reynolds number and also Nusselt number to characterize the convective transport of heat, that is flow and convective transport of heat outside the cylinder, we can simply use forced convective heat transfer model outside the cylinder, and though radiation or radiative transport of heat is not significant as the convective heat transfer is, still we could mathematically quantify the expression of this quantity, expression of this transport of heat, and we had seen that due to that significant temperature difference between gas and wall, sometimes this quantity that is radiative transport of heat may become significant. Now, what we could not discuss today is, if we look at that the amount of energy which is getting lost or which need to be transferred is through the coolant, through the oil, through ambient, I mean directly to the ambient. Also another significant part is loss of energy or loss of heat through the exhaust gases, which we need to know, and though intake manifold is integrated to the engine block, and rise in temperature because of the combustion is also getting transferred through intake manifold, that part we did not discuss today. So, in the next class we shall be discussing about the loss of energy through the exhaust gases into the ambience, and the transport of heat or transfer of heat or removal of heat due to combustion process through the intake manifold. Whether that heat is directly exposed or directly transferred to the ambience, or that heat is again somehow is taken back to the inflow of air or inflow of fuel, that part we will discuss in the next class. And we have discussed about the transport of energy by the oil, that oil is lubricating oil, and this heat transfer directly to the ambient, that we have discussed today, this fellow, that Q dot 4, because this quantity is not taken into account in this expression, but still this is an important quantity and we have quantified. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.